I am Raghavan, Chemistry faculty from Alfords College. I welcome you all for the Alfords Chemistry e-learning classes, session 15th. Okay, in the last session, that is in session 14th, so we had some discussion about Bohr's theory, numericals we have done. Okay, so today also let us see some important concepts of hydrogen spectrum and Bohr's theory also. Okay, fine. So now, according to the Bohr's theory, Bohr's atomic model can explain the atomic spectrum of one electron containing species only. Okay, so for example, if the question is like, so Bohr's theory can explain the atomic spectrum of all the species except, Bohr's theory can explain the atomic spectrum of all the species except, that is the question. Options I will give like this. Options are, for example, He plus, second option, let us take He, third one is lithium 2 plus, and fourth one is H, hydrogen atom. Now, so Bohr's theory can explain the atomic spectrum of one electron containing species. That means let us see how many electrons are there in H plus ion. H plus ion is containing only one electron because it is H plus cation. That means it has lost one electron. Okay, beryllium, that is helium, atomic number 2, it contains 2 electrons. Okay, it's a neutral atom, it contains 2 electrons. Lithium, atomic number 3, after losing 2 electrons it becomes plus 2. So therefore this ion contains only 1 electron. And hydrogen atomic number is 1, therefore it contains 1 electron. So Bohr's theory can explain the atomic spectrum of He plus, lithium 2 plus and hydrogen atom, but cannot explain helium atom because it contains 2 electrons. Okay, like that we can expect a question, theory question like this. Okay, and next let us see Bohr's theory. According to Bohr's theory, the radius of hydrogen atom, that means let us see the competition window, that is radius, okay, the radius of nth orbit of hydrogen atom, nth orbit, radius of nth orbit is equals to, that is radius of the first orbit into n square by z, okay, that is the brief representation of the calculation of the radius of nth orbit of species containing 1 electron. Okay, it is applicable for all, right? Say for example, let us take question, radius of first orbit of hydrogen atom, radius of first orbit of hydrogen atom is r. How much is saying? R. Okay, what is the radius of the first orbit of lithium 2 plus ion? Okay, calculate, that means the radius of first orbit of lithium 2 plus. Okay, radius of first orbit of lithium 2 plus will be how much? Okay, options I will give that this. First option, say it is 9r. Second option, 3r. Third option, r by 3. Fourth option, r by 9. So now apply that concept. So radius of the third orbit, that is first orbit of lithium 2 plus. Okay, radius of first orbit of lithium 2 plus. Okay, that is equals to radius of the first orbit, how much? R, he said, r into n square, that is first orbit only, by z, atomic number of lithium 2 plus is 3. So therefore that gives r by 3, that is radius of the third orbit of lithium 2 plus is third option, r by 3. So that logical approach, the numericals, very simple numericals, okay, if the basic fundamental concept is clear, so without any mistake, so you can answer the simple questions like this, okay. And let us see some more, okay. So is it clearly understood? Okay, in this what is asking? Radius of first orbit of hydrogen atom, how much is saying? He is saying is this r. Next, what he is asking us to calculate? Radius of first orbit of lithium plus 2 he is asking now, okay. That will be, we have to find, okay. That is radius of first orbit of lithium 2 plus is equals to radius of the first orbit, okay, into n square, first orbit only, that is 1 square, by z is atomic number of lithium 2 plus 3. So r by 3, like that is why it is third option, okay. Now another concept, let us take another concept. Yes, another concept. Which of the following will have the same radius? Which of the following has the same radius as that of first orbit of hydrogen atom, as that of first orbit of hydrogen atom, okay. That is radius, first orbit of hydrogen atom radius, okay. Question once again, which of the following has the same radius as that of first orbit of hydrogen atom radius, okay. So options, let us take up. Helium plus n is equals to 2. Helium plus n is equals to 2. Second option, lithium plus 2, n is equals to 2. And third option, let us take it, lithium plus 2, n is equals to 3. And fourth option, so helium, lithium completed. Let us take beryllium plus 3, n is equals to 2, okay. So these are the options given for us. Now let us work out what is the question. The radius of the following has, that is which of the following has the same radius as that of radius of the first orbit of hydrogen atom, as same as that of radius of first orbit of hydrogen atom, okay. What is the first orbit of hydrogen? Sir, it is first orbit of hydrogen, say it is r1, whatever it is, okay. Instead of specifying the value, that is like 0.529 angstroms, let us say it is r1 or simply r, okay. Now as per the, apply this one. So radius of second orbit, n is equals to 2, radius of second orbit of helium, okay. So it is equals to r1, that means radius of hydrogen atom in first orbit, into 2 square, that is 4, by helium atomic number is 2, so it is 2 za. So the radius of second orbit of helium plus 2, the radius of second orbit of helium plus 2 is twice the radius of the first orbit of hydrogen. So this is not the answer for us. Okay, now you got it clear, okay. Moving to the next, to second option, okay. Be careful. Now radius of the second orbit of lithium 2 plus, radius of second orbit of lithium 2 plus, okay, that is equals to radius of first orbit of hydrogen, yes, into 2 square, that is 4, by lithium atomic number is 3. So it is not exactly r, okay. Therefore it is not, even second option is also not correct. Now coming to the third option, okay. So radius of third orbit of lithium 2 plus, that is equals to or radius of first orbit of hydrogen atom into 3 square, n square, 9 by 3. So it is 3 times. Okay. Now coming to the fourth option, this is not the answer for us. Now coming to the fourth option, be careful in this. Radius of second orbit of beryllium plus 3, that is equals to radius of first orbit of hydrogen atom into 2 square, that is 4, by beryllium atomic number 4. Ones of 4 cancelled. So now the radius of second orbit of beryllium plus 3 is equal to the radius of first orbit of hydrogen atom. Therefore, the fourth option is the right answer for us. Okay, is it the concepts are clear? Okay, so these are the simple questions, simple objective questions for EAMCET examinations and mains examinations, and you can also expect such type of simple easy questions for BITS Pilani also. Okay, BITS Pilani examinations. See, in the BITS Pilani examinations, you don't find the lengthy calculations, you will find only the simple logical answers. Okay, so in that we have to maintain only the time management, we have to see in that. Okay, right. So this is the concept for the given question. Very good. Now let us, these are concerned with the radius. Okay, now let us move into the hydrogen spectra, right? Hydrogen spectra. Okay, now the concept, I think it is clear. Okay, right. Moving to the hydrogen spectra numericals. Hydrogen spectra. So Bohr's theory can explain the atomic spectrum of, it explains spectrum of, okay, it explains spectrum of the species containing, it explains the spectrum of species containing only one electron. Okay, Bohr's theory explains the spectrum of the species containing only one electron. That should be remembered. Okay, because if the species containing, it may be atom or it may be ion, whatever it is, if the species containing more than one electron, so Bohr's theory will not take the responsibility to explain the spectrum of that species. Okay, right. Now coming to the hydrogen spectra. Okay, hydrogen spectra, there we have some logical approach formulas like let us have, these are the orbits. Okay, first orbit, second orbit, third orbit, fourth orbit, fifth orbit, like that. Okay, these are the orbits. For example, I am taking, this is a first orbit, it is second orbit, n is equals to 2 and n is equals to 3, n is equals to 4, n is equals to 5, n is equals to 6. See, already these numericals already completed. Just once again I am revising all these numerical points. Okay, now so in this, when electron is jumping from, sixth state, that means when electron normally present in the first orbit, by absorbing photon energy, what happens? The electrons get excited to the higher energy levels. So to which energy level it is excited? It is excited to sixth orbit, or make it, instead of sixth, let us make it 4, 5 orbits only. Okay, the electron excited from normal ground state to fifth energy level. Okay, fifth energy level. That excited electron in the higher energy level is quite unstable. That means it is unstable, it should come back. So that means it undergo de-excitation. That means this excited electron will come back to the normal ground state, that is n is equals to 1, directly in one step or in several steps. Okay, the de-excitation of the excited electron can take place directly in one step or in several steps. Okay, so during de-excitation process that emits radiation, the emitted radiation when passed through the prism, the dispersed spectral lines are noted on photographic plate. So that is called hydrogen spectrum. So we know the definition very well about the hydrogen spectrum. Already we had done that. Now we are concentrating on the number of spectral lines now. Okay, that is a point. Now the concept 1, that is when excited electron jumps from any higher energy level, whatever it may be 6th orbit, 7th orbit, 5th orbit, 4th orbit, whatever it is, the excited electron when jumps from higher energy level to first orbit, higher energy level to first orbit. Okay, got it. Now the example I am taking here, example, that is n is equals to 5 to n is equals to 1. That means now the electron is jumping from fifth orbit to first orbit. How many maximum number of spectral lines appear in the spectrum? How many maximum number of spectral lines? Maximum number of spectral lines. That is maximum number of spectral lines. Maximum number of spectral lines when electron jumps from nth orbit to n is equals to 1. Nth orbit to n is equals to 1. Be careful, you should remember that. That is equals to n into n minus 1 by 2. N into n minus 1 by 2. That means n is equals to higher energy fifth orbit. 5 into 5 minus 1 by 2. That is equals to 5 into 4 by 2. That means 10. 10 spectral lines are formed. Okay, concept you should remember. What is that concept? When electron is jumping from higher energy nth orbit to first orbit, nth orbit to first orbit, nth orbit to first orbit, the maximum number of possible spectral lines appear in the spectrum. That is n into n minus 1 by 2. Okay, that is 10 spectral lines. 10 spectral lines. So like this, say we can say the same line should not be repeated. If it is repeated, we should not count. Okay, let us see. This is 1. And second, what we can say? Second is like this. 1. So it can jump in different stages. Okay. 1, 2, 3, 4, 5. Okay. These are the things possible. Okay. It is already repeated in this, so it is not counted. So it is going back directly to the ground state. So it is 5, it is 6. Next one, it is not repeated. 7. So 2 to 1, 3 to 1, it is not repeated. So 8. Next one is not repeated. 9th, and it is from 2 to 1, it is already repeated, so not counted. One more, already repeated, not counted. That is 4 to 2, nowhere it is repeated, so 10. So 2 to 1, already repeated, not counted. So total maximum number of possible spectral lines are 10. Okay, that is 10. So when electron is jumping from nth orbit to first orbit, the maximum number of spectral lines appear in the spectrum, hydrogen spectra, is equals to n into n minus 1 by 2. Okay, so that is example, and we have explained with this. Okay, next, this is the concept. Okay, understood, right? Coming to the next concept, next logical approach, let us take up. Okay, done. Have you seen this? Okay, the same line should not be repeated. Here it is repeated. Okay, adjacent, repeated. The same line should not repeat. And here, this line already here we have, that is 2 to 1. It's again 2 to 1. So it should not be counted. It is not counted. Here already is repeated, not counted. Okay. So like this, maximum number of spectral lines. Now moving to the next concept, next logical approach. Okay, so it is done. Let us take up what is that? When electron is jumping from higher energy levels to, that is nth orbit to middle orbit, say for example second orbit. So the previous one is the electron is jumping from higher energy levels to first orbit. It is coming back to the ground state. Now, in the second case, it's not coming back to the ground state. It is dropped at middle energy levels. Okay, that is second concept. Nth orbit to, say for example, n is equals to 2. N is equals to 2. Okay, this is now the maximum number of spectral lines maximum number of spectral lines when electron is jumping from nth orbit to middle, that is n is equals to 2, like this. So that concept is equals to, that is the logical approach may be different, okay, but the ultimate concept will be same. So that is higher energy level minus lower energy level into higher energy level minus lower energy level plus 1 by 2. That is approach. Okay. So first, see, understanding is different and remembering is different. So once the concept is clearly understood, please make a note and remember it perfectly. Okay. Now let us take the same example, that is electron is jumping from 5th orbit to 2nd orbit. 5th orbit to 2nd orbit. So example, electron is jumping from n is equals to 5 to n is equals to 2. N is equals to 5 to n is equals to 2. So the maximum number of possible spectral lines appear, that is equals to, that is 5 minus 2 into 5 minus 2 plus 1 by 2. Okay, that is approach. Okay, now here it is 5 minus 2, that is 3, and it is 5 minus 2, 3 plus 1, that is 4 by 2, that is equals to 4 3 is 12 by 2. 6 spectral lines are possible. 6 spectral lines are possible when electron is dropped at second energy, that is in the middle orbit. That is a concept. So this is the first concept you should understand, and this is the second concept we should understand this. Okay. So here it is, the excited electron is coming from nth orbit to first orbit, and in this case nth orbit to second orbit. Okay. The concepts are clear, because these are the important logical approach points for the objective examinations. Okay. Understanding the concept is very simple, easy on the board, but unless you practice, it is difficult to remember them. Okay, right. Now coming to the another one, let us make a question. Let us make a question, then we'll explain on that. Okay. How many spectral lines are possible? Let us write. How many spectral lines are possible, or you can say formed. How many spectral lines are formed when electron jumps from n is equals to 5 to n is equals to 1. Okay, listen the question, don't rush to answer that. Okay, when electron jumps from 5th orbit to 1st orbit, see, the excited electron can come down to the ground state, so directly in one step or in several steps. So as a result, we can expect more number of spectral lines. Okay, now the condition is, okay, when the number of spectral lines in the Bohr series are completely not formed. Assume that when Bohr series is exempted, not formed. Okay, when second energy, that is when Bohr series not found, that means you are imagining the condition. We cannot say that it is formed like this, because the excited electron during de-excitation process, the spectral line should appear in all the regions of hydrogen spectra. Okay, but the condition in the problem is saying that when Bohr series is not formed, means we have to assume the question when Bohr series is not formed, not found. Okay, so how many spectral lines appear in the hydrogen spectra? Okay, that is the concept. Okay, based on the concept of the given question, what is the answer? Yes, let us take that 5th orbit to 1st orbit. 5th orbit to 1st orbit. 1, 2, 3, 4, 5. 5th orbit to 1st orbit. Okay, fine. But Bohr series is not found. That means we should neglect the Bohr series, means 2nd orbit. Let us neglect one orbit. Okay, fine. So now this is n is equals to 1, this is n is equals to 3, n is equals to 4, n is equals to 5. 5 orbits, that is 5th orbit. Because to avoid confusion, I completely removed the Bohr series 2nd orbit. Now you can check. So 5th orbit to 1st orbit is possible direct transition. Next to 4th orbit to 1st orbit is formed with direct transition, and 3rd orbit to 1st orbit is also possible. Okay. Next 5 to 3 is possible, and 4 to 3 is also possible. Next one more, 5 to 4 is also possible. Total how many spectral lines are formed? 1, 2, 3, 4, 5, 6. So 6 spectral lines can appear like this. Okay. In the hydrogen spectra only, we explain in different concepts only. That is, excited electron is coming back to the 1st orbit, number of spectral lines. Next, excited electron is coming back to the nth orbit, not ground level, that not 1st orbit. Okay, that this formula, okay, this concept we have to follow. Okay, now 3rd concept is, so when this type of questions, that is, so during this process we can expect the maximum number of questions like this, maximum number of spectral lines. But what is the condition mentioned in the problem? So they said that when there are no Bohr series spectral lines found in the series, we have to assume that. Okay, so when there are no Bohr series means completely the 2nd orbit is completely neglected. Okay, that is why, so total possible spectral lines according to the given question condition is 6 only. Okay, like this we can expect questions from hydrogen spectra. Okay, that is spectral lines, hydrogen spectral lines. Now let us see the Bohr equation and Rydberg's ridge equation. Okay, let us work on that. That is another important concept from this area. Okay, so in hydrogen spectra, as we know that hydrogen spectra is the simplest atomic spectrum of all elements because hydrogen atomic number is 1. So 1 electron containing species. So 1 electron containing species in the spectra are given this many lines. So that is Lyman series, Bohr series, Paschen series, bracket series and Fund series. Okay, these many spectral lines are found. Okay, now let us work like this. Bohr equation. To calculate wave number, nu bar is equals to 1 by lambda, that is equals to R H, that is Rydberg's constant value for hydrogen, into Z square 1 by N1 square. Okay, say Bohr equation, strictly speaking the Bohr equation, that is Bohr series is formed in 2nd orbit. So that is why it is 2 square minus 1 by N square, where N is equals to excited levels. What are the excited levels to the 2nd orbit? 3 and above. So N is equals to greater than 3. That is, it may be 3rd orbit, 4th orbit, 5th orbit, 6th orbit, whatever it is. Okay, so this is the Bohr equation we can use. Okay, next one is Rydberg's equation. Rydberg's equation, that is Rydberg's ridge equation. Rydberg's ridge equation. Okay, so Rydberg's and Ridge, they are scientists. Rydberg's and Ridge, they proposed the equation, that is nu bar is equals to 1 by lambda is equals to Rydberg's constant value for hydrogen into Z square. The same concept we have to explain. So this equation is applicable only for the Bohr series, and Rydberg's ridge equation is applicable to any spectral line in the hydrogen spectra, any series, any spectral line of any series in the hydrogen spectrum, that is into 1 by N1 square minus 1 by N2 square. N1 square minus 1 by N2 square. Okay, this is the equation format. Okay, now what we can calculate by using this? We can calculate wave number. Okay, please do note at this. What are the things can be calculated by using this equation? We can calculate wave number. By using this wave number, we can also find wavelength. Okay, wavelength. And so what is RH? That is RH, Rydberg's constant value for hydrogen. How much it is? 109,677.8. Make it round figures, that is 109,678 centimeter inwards. That means the units of Rydberg's constant value is equal to the units of wave number. Okay, that should be remembered. So Z is equals to atomic number of that species containing one electron. Okay, where N1 square and N2 square, we should remember that N1 is the ground state of the series. N1 is equals to ground state of the series, and N2 is equals to excited level of the series. Okay, I will give only one example. Okay, try to remember only one example I will give. For example, calculate wave number of H beta spectral line. H beta spectral line in Lyman series. Okay, that is the question. In Lyman series, let us substitute. Nu bar is equals to RH, that is Lyman series of helium plus, let us consider helium plus ion. Okay, that is a complete question. So nu bar is equals to RH. R is equals to 109,678 centimeter inwards into helium atomic number is 2 square. Okay, that is 2 square into, it is H beta spectral line. Okay, H beta spectral line means 1, 2, 3, 4. So the first line is H alpha, the second line is called H beta line. That means N1 is equals to 1 and N2 is equals to 3 by 1 square minus 1 by 3 square. Okay, so the electron is coming from third energy level to first energy level. Okay, on simplification you will get lambda, that is nu bar you will get. Okay, nu bar. Then we have to calculate. Okay, calculate wave number. That is wave number we can calculate like this. Suppose if you are calculating wavelength, that is lambda is equals to 1 by nu bar. So reciprocal of that we can calculate wavelength also. Okay, like this numericals we can expect from hydrogen spectra. Okay.